Hello everyone, welcome back to my YouTube channel. In this particular video, we'll be looking into the loss function that Perceptron uses. Loss function is extremely important. We can reach to the most optimal solution with the help of loss function. But before that, what exactly this loss function is, let's have a look at it. So first, let's see what exactly loss function means. So by the definition, loss function measures the difference between predicted and actual values, guiding the model improvement. By this definition, you might have got that loss function is same as error. Yes, it measures the difference between what exactly is the prediction and what was the actual value for it. Now, why we use this loss function? Because we can reach to the most optimal solution with the help of this loss function. And how we can reach to the optimal solution, we are going to look at it with the help of an example. So here let's say we have this particular axis and we have these data points. You can clearly see we have two classes. One is the class of blue circles and another is the class of pink circles. You can see there are certain misclassifications in this particular classes. Let's say the data points that lie in the class of blue circles are positives. We can denote it by 1. And the data points which are lying in the class of pink circles are negative and are denoted by 0. We have this particular classifier. It is nothing but the Perceptron classifier, which we have already seen how we can classify two classes with the help of Perceptron algorithm. We also have seen the implementation of Perceptron algorithm from scratch. If you haven't watched that particular video, please go and watch in the deep learning playlist. Now, considering this particular classifier, if we consider this particular misclassified point, you can see in the class of blue circles, we have got this pink circle. And if we try to calculate the error for this particular misclassified data point, what exactly it will be? We already have seen the formula for finding out the error. It is nothing but the actual value minus the predicted value. Here the actual value is 0 because it should lie in the class of pink circles. And the predicted value is 1 because it has came into the class of blue circles. So the error or the loss will be 0 minus 1, which is minus 1. Similarly, if we consider this particular misclassified pink circle, again for this particular data point, the actual output has to be 0 and the predicted output here is 1. So the error is 0 minus 1, which is minus 1. You can see for both these misclassified data points, the magnitude of the error is same. If you carefully observe, this particular misclassified point is at a larger distance from the hyperplane or the classifier when we compare it with the another point. So don't you think that for this particular misclassified point, the error has to be more than the other point? Pause the video and think about it. Similarly, if we come to this particular class, here again we have two misclassified data points. If we consider this particular misclassified data point, the actual output here is 1 and the predicted output is 0. So what is the error? It is 1 minus 0, which is equal to 1. Similarly, in this particular class, you can also see one more misclassified data point, and again the actual output has to be 1 and the predicted output for this data point is 0. You can see 1 minus 0 is 1. Now for all the 4 misclassified data point in both the classes, the magnitude of the error that has occurred for all these data point is 1 for all. Just ignore the sign, whether it is plus or minus, just ignore that. But just focus on the magnitude. It is 1 for every single misclassified data point. And this particular concept where all the misclassified data point will be having the loss 1 is termed as 0-1 loss. So specifically in this type of loss, all the misclassified data point will be given the error value as 1 and all the perfectly classified data point will be given the error value as 0. So here you can clearly see we have total 4 misclassified data point. So that is why the total error using the 0-1 loss is 4. Using the 0-1 loss technique, we have got the total error as 4. Now what if we change the classifier? You can see over here we have changed the parameters of classifier in such a way that it is different from the older one. Still, you can see that now also we have 4 as the total error. There is no change in the total loss even if we have changed the orientation of the classifier. Similarly, we can have multiple such classifiers which can classify these two classes, and you can clearly see for all these classifiers which are classifying these two classes, the total error using this 0-1 loss technique is 4. So do you think that this particular 0-1 loss technique is anyhow going to help us to find out the most optimal classifier which will classify these two classes with the minimum possible loss? Obviously not, because every time we change the classifier, you can see that the total loss remains the same. This is not going to help us to find out the most optimal classifier, and that is why in Perceptron we cannot use 0-1 loss as the technique to optimize the classifier. We will have to choose a loss function which is going to alter the loss as and when the classifier is changed. So there are different loss functions which are used for classification techniques. Some of them are listed below. We have cross entropy loss, which is also called as log loss. Then comes the binary cross entropy loss. Then we have categorical cross entropy. Then we have sparse categorical cross entropy. Then we have hinge loss and focal loss. We are going to look at all these losses as and when it is required, but for now just remember that the perceptron algorithm specifically uses the hinge loss. Now why it uses hinge loss, what makes this particular loss special, so that the drawbacks that 0-1 loss had were solved. We will be looking into every single thing related to hinge loss now. So first, let's have a look at the hinge loss formulation. So hinge loss is given by this particular formula. You can see in the left hand side, the hinge loss is denoted by L of x, y and w, because it is a function of these three parameters x, y and w. And on the right hand side, you can see how to solve this particular loss function. It is max of 0, comma, the expression which is minus y multiplied by wx plus b. Now what exactly all these parameters are? You are already familiar with this. X is the input feature vector. In a particular given data set, all the input features comes under x. Next we have the parameter y. Here y is denoted as true label. Note this word true label, which means the actual output and not the predicted output. And also make sure one thing, that here we represent the class label as 1 or minus 1. Here it is not 1 or 0. We specifically choose minus 1 to represent the negative class. Always remember this thing. And now the next parameter is w, which is nothing but the weight that is associated with the feature input. Next we have the bias term, which is nothing but the weight that is associated with the virtual input x0. So I hope now you are familiar with this particular equation. Now we are going to look the detailed intuition behind this particular equation, how it is going to help us to find out the loss and how the loss differs for every single misclassified data point. Here we are going to take this particular example. You can see we are denoting the negative class by minus 1. Let's say the equation of this particular line, which is nothing but the classifier, is 4x plus 5y minus 12 equals to 0. 4 and 5 are the weights associated with the feature inputs x and y respectively, and minus 12 is the bias weight for this particular classifier. Now, if we carefully consider this particular data point which is misclassified, let's say the coordinates of this particular data point is 4, 1. Now we are going to find out the loss of this particular data point with the help of the hinge loss formulation. Now, for the data point 4, 1, we have to find out the value of the loss. So first we have to calculate the value of this expression minus y into w into x plus b. If you remember, w into x plus b is nothing but the expression which was the weighted sum in the perceptron. We already have seen many examples to find out the weighted sum. Here we have the coordinates 4, 1, that is nothing but x, y. And we also have the equation 4x plus 5y minus 12. So you just have to plug in the values 4, 1 instead of x, y in this particular expression 4x plus 5y minus 12. that will be your wx plus b, and minus y is nothing but the actual output of this particular data point, which is nothing but negative, which is -1. So here you can see instead of y we have written -1, and instead of wx plus b we have written 4 into 4, which is nothing but 4x, because x here is 4, and then 5 into 1 because it is 5y, and y here is 1. In the coordinate you can see 4 comma 1, so y is 1, and then minus 12 is the bias term. So I hope this particular expression is clear to you all. Now we will calculate this. You can see that minus 1 into minus 1 is 1, and in this particular expression 4 into 4 is 16, 5 ones are 5, minus 12 remains as it is, and when we calculate this we get 9. 1 multiplied by 9 is nothing but 9. Now you can see that the value of this particular expression in the max function, we have got it as 9. Now we'll put this value 9 in place of the expression minus y into wx plus b, so it becomes max of 0, 9. Now you know that maximum from 0 and 9 is 9. That is why the loss which is associated with this particular coordinate 4, 1 is 9. So this is how we calculate the hinge loss for any data point which is misclassified. Similarly, let's consider this particular data point now, 3, 4. Let's calculate the loss that is associated with this particular data point using the hinge loss formulation. We have the expression again, but now here we have the values of x and y as 3 and 4 respectively. So let's plug in the values in this particular equation. You can see in 4x plus 5y minus 12 we have plugged in the values 3 and 4 in place of x and y. And also make a note that the value of y is -1 because here the actual output has to be -1, which is nothing but the negative class. So after calculation, we get the final output as 20. So 20 is the value of this particular expression, and when we plug in the value of this expression in the max function in place of this expression, we get maximum of 0, 20. Now maximum of 0 and 20 is 20. So you can see the loss associated with this particular data point 3, 4 comes out to be 20. And you can see that the loss associated with both these data points are different, which was not in case of 0, 1 loss. Here you can clearly see that the coordinate 3, 4 is at a higher distance from the classifier when we compare it with the coordinate 4, 1. And that is why the loss also has to be more than the coordinate 4, 1. And you can see we have got the same. We have got more loss for the coordinate 3, 4 when we compare it with the coordinate 4, 1. And this proves that the hinge loss formulation is going to provide different loss values for different misclassified data points. And that was the goal which we have achieved. Since we are going to get different loss values for different misclassified data points, this is surely going to help us to optimize the classifier. Now similarly, if we look at the other class, you can see this particular class contains two misclassified data points. For the first misclassified data points, the coordinates are 0, -2, and if we try to calculate the loss associated with this particular misclassified data point 0, -2, we can get this particular expression. You can see in place of y we have written 1 because the actual output for this particular data point was supposed to be 1. Now if we plug in all the values and we calculate the value of this particular expression, we get 22. Now if we replace the value of this expression with 22 in the max function, then we can get the maximum value from 0 and 22 as 22. So you can see the loss associated with this particular coordinate 0, -2 is 22. Similarly, if we look for the next point, which is -6, 0, if we calculate the loss here is 36. You can see we are getting different loss for different data points. Also, the data point which is closer to the classifier is having less loss than the data point which is at a higher distance from the classifier. So I hope it is clear how we can calculate the hinge loss for all the misclassified data points, and all the values will be different for all the misclassified data points. But now what about the data points that are correctly classified? For that, what is going to be the hinge loss value? Let's have a look at it with the help of an example. Now, in this particular case, let's consider this particular data point which is correctly classified. The coordinates of this particular data point is 5, 2. Now we are going to calculate the hinge loss for this particular data point which is correctly classified. So you can see here the actual output for this particular data point is 1. So in the particular expression, in place of y, we are going to write 1 because the actual output is 1. And in the expression 4x plus 5y minus 2l, in place of x and y, we are going to write 5 and 2 respectively. Now when we calculate the value of this particular expression, we get 4 5s are 20, 5 2s are 10, and minus 12 as it is. When we calculate it further, we get minus 18 as the final output. This was the output of the expression. Now if we plug in the max function, we get maximum of 0, minus 18 as 0. So here you can clearly see that the hinge loss for this particular correctly classified data point is coming out to be 0, and same case will happen for any correctly classified data point. So I hope it is clear how this hinge loss formulation is going to tackle both the scenarios where the data point is correctly classified or it is misclassified. For all the correctly classified instances, the hinge loss will be 0, and for incorrectly classified instances, the hinge loss is going to be greater than 0. Now I am sure that this particular example has cleared all your doubts. But you can see that we have only seen the formulation for a particular instance. What will be the loss of a single instance? We haven't seen yet what is going to be the total loss for the entire classifier for all the data points. So to calculate the total hinge loss, there is a slight change in the formula. So the formulation is given by this: L of x, y, w, which is nothing but the function, is equal to 1 by n. Here n is nothing but the total number of data points that is present in both the classes, and this 1 by n is multiplied by the sum of the loss that is associated with every single data point which is present in both the classes. So here in this particular case, we can clearly see that we have total 26 data points. That is why we have written 1 by 26 in place of 1 by n. And since we had only 4 misclassified data points, and the loss associated with it is 9, 20, 22 and 36. So we have written it over here, and then we have written 0 plus 0 and so on, which is nothing but the loss associated with the correctly classified instances. And when we solve it, we get 3.35 as the total loss. So this total loss is going to be the loss associated with this particular classifier. And with this particular total loss, we can compare two different classifiers and we can say which one is the better. The lesser is the loss value, the better is the classifier. So now we are going to use this particular hinge loss function, with the help of which we can find out the optimal classifier now. Now for reducing the loss, we'll have to alter some of the parameters. If you remember, the loss was dependent on the parameters x, y and w. So somehow we have to alter this particular parameters in such a way that the immediate next loss is going to be lesser than the current loss by updating these parameters. As you know, this is the total loss function. To get the optimal classifier, we'll have to minimize this particular total loss function. You can see by altering the values of w and b, we can minimize this particular loss function. Now before moving on to the point how we can do so, first you need to make sure this thing that the weights and bias are only updated whenever misclassified points are encountered. For any correctly classified point, the weights or the bias is not going to update. And also you can see one thing, that in this particular entire function, there is only a single expression which is important, and on this expression only we are going to work on. And also we have seen that the value of this particular expression is going to be positive only when we have misclassified data point. For any correctly classified data instance, the value of this particular expression is going to be negative. So by using this particular expression, now we'll try to update the weights, and we can update the weights to reduce the loss with the help of the gradient descent functionality. The gradient descent functionality is so amazing that it can be used to optimize the model. Now here in Perceptron also we can use this method to reduce the loss, and thus we can easily find out the optimal classifier in Perceptron also. Now what exactly happens in this gradient descent methodology, let's have a look at it. To reduce the loss, we have to find out a particular value by which we can reduce it, and that particular value can be found out with the help of slope. We can find the slope for any particular point by differentiating the entire loss function. If you remember that particular highlighted expression, we can differentiate that particular expression with the weights. Let's say we are differentiating with w. So we are going to find out the partial derivative of the loss function with respect to w, and then whatever value we get of this particular partial derivative, we can then use that particular value to adjust the current parameter. Basically we subtract the old weights with this slope, and you need to continue this process unless and until the global minimum is found. That means the loss is minimum from all the others. You can see we can update the weights and bias with the help of this particular formulation which we have discussed now. Here you can clearly see the formula W new, which is the new weight, is equal to W old minus eta, which is the learning rate. Now we already have discussed this particular term learning rate, multiplied by dou L by dou W. It is nothing but the partial derivative of the loss expression with the parameter W. Here we can update the weights with the help of this particular formula. Now we multiply this learning rate eta with the slope just to avoid the drastic change in the weights. We will have to choose an optimal value of the learning rate eta. It must not be smaller, it must not be larger. Generally the range for eta value is 0.0001 to 0.1. Now if we look at this particular partial derivative, if we try to solve this, what we get? Let's see. Here you can see that the loss function L is nothing but the expression minus y multiplied by wx plus b, and we are now going to differentiate it with the parameter w. Note one thing, that partial derivative means whatever parameter you are using for differentiating, only that parameter will be acting as a variable and all other parameters will be acting as a constant. So here you can see that y, x and b, all these parameters will be acting as a constant. Being it as a constant, we can take minus y outside the brackets, and then we can differentiate the term wx and b separately with respect to w. So you can see that here x is a constant, that is why the differentiation of w multiplied by x with respect to w will be x, since x is a constant and w is the variable, and we are differentiating with the variable w only. So the differentiation will be x, and the differentiation of b with respect to w is going to be 0 because b is a constant. Now you can see minus y was outside of the brackets, and inside the bracket we are only left with x. Minus y into x comes out to be minus yx, and therefore you can see the value of the partial derivative of loss with respect to the variable w is minus yx. Now if you plug in the value of the dou L by dou w in the original expression, the expression will become something like this. W new will be equal to W old plus eta multiplied by y multiplied by x, and this particular expression will update the weight, and the weight will be updated in such a way that the output of the loss function will reduce, which will in turn optimize the classifier. I hope the entire derivation and the concept is clear. Now this was when we are updating the weights. What about bias? So for updating bias, we have this particular formula, b new equals to b old minus eta multiplied by, this time here the partial derivative will be with respect to the variable b. The value of the loss expression is same. You can see it is minus y multiplied by wx plus b. Here now we will be differentiating this particular expression with the variable b. Here we are going to find out the partial derivative. That is why all the parameters except b, which are y, x and w, are going to be constant. And therefore we can take minus y out, and inside the brackets we can separately find out the partial derivative of wx and b with respect to b. You can see w into x, both these terms are constant, and we know that the differentiation of a constant term is 0. So it is coming out to be 0. And next, the differentiation of b with respect to b is going to be 1. So minus y multiplied by 0 plus 1 multiplied by minus y comes out to be 0 plus minus y, which is minus y. So here in place of dou L by dou B, you can replace the value as minus y in the expression. So you get the final expression as B new equals to B old plus eta into y. Note that the y is the true label, which is the actual output. So now I hope it is very much clear to you all about this particular derivation and the concept of updating the weights and bias using the gradient descent methodology. Now the question comes, till what point we need to update these weights? You can update the weights and bias until the loss gets 0 or it becomes nearly equal to 0. Whenever the loss gets 0, the model converges. But if in case the model is not getting converged, or if the loss is not getting 0, then in that particular case, we can stop the iterations whenever we come across the least value of the loss, which is almost equal to 0. So now I hope it is clear that what exactly hinge loss is and how this loss function are actually helpful to optimize the model. We also have seen the gradient descent technique through which we can update the weights and we can reduce the loss. I hope everything is clear. If you guys have any single doubt, you can post it in the comment section. Also, you can post your reviews and suggestions for this particular video. Please share this video with your friends as much as possible. For more such videos, do like, share and subscribe to my channel. Also hit the bell icon. Don't forget to follow me on Instagram and also follow me on Telegram.